All right, so today is our 8th session, September the 8th. This is in full screen. Today we're going to be talking about the other tools that are used in basic front-end development. We're not actually going to be making any rudimentary websites. I just wanted to go over what they are and what you're likely to be exposed to in your time in the Platoon cohorts. So the front end, which is in what you tend to build if you are a front-end web developer, is the thing that you actually see. It's the website itself, not all the logic and programming stuff in the background, which we've been building the skills for this entire time. The vanilla front end is made with 3 components: HTML, CSS, and JavaScript or JS, although you do not require JavaScript to make a website. And I'm going to talk about what HTML and CSS are shortly. Now, technically, these are all you require to make a website. However, modern web development uses frameworks such as React and Bootstrap, which are the tools you're going to be using in Platoon. Right. So HTML stands for the Hypertext Markup Language. And this is an example of what HTML looks like here in the bottom left corner. So HTML is not used for programming. It doesn't have for loops, it doesn't have variables, and it isn't used to express logic. It's used to describe what the website looks like at a very, very high level. It specifies the order in which things appear on the page, like images and text. So here we have the word hello world before an image is put on the screen. So if you look at this picture over here, this is the picture that is generated from this code. And you see the word hello world is put before the image on this website. That's a picture of my dog, by the way. So I have this on my computer. I already have the dog in this folder called images. And this code right here is in a file called index.html. HTML files are files that contain this HTML code, and they end in .html, just like JavaScript files end in .js, and CSS files end in .css. So I don't expect you to be, familiar with HTML at all. You're not going to be writing any HTML or CSS today. I just wanted you to be aware of what it is. And it specifies the order in which things come into the page. All right. Now, CSS stands for Cascading Style Sheets, and they allow you to fine-tune and change details as specified from HTML. So CSS doesn't really exist on its own. It does something to HTML, and it makes it look pretty. It styles the elements. These individual little tag things are called elements. And these elements may include text, and we can change elements of the text, like how big it is, or where it's positioned along that row, or the font that it has. Is it bold? Is it italicized? Those are all things we can change with CSS. And for images, we can also change the size and relative positioning, in addition to maybe rounding the edges or adding a filter. These are things that can be done in CSS. So we can have a CSS file. Again, it doesn't matter what you call the CSS file. Some people will call it index, some people will call it main. Some people may have multiple CSS files. Here we have some HTML code, which is using the CSS file to modify itself. So I'm saying use the contents of the CSS file. I haven't shown the contents of that file yet. I will in the next slide to modify this existing code, which we already had. It's just hello world and a picture of the dog. So this is what it looks like after applying the following CSS using the linking method that we previously described. Here I say take the paragraph and give it this font. And you can see a big list of all the fonts and what they look like that you're able to use in CSS. And I also made it bigger. Same for the image. I made it smaller so it doesn't take up the entire page. And I also rounded the edges a little bit. And if I made this a bigger number, it would be rounded even more. So that gives you some idea of what CSS is capable of doing. Yeah, so that's all really. Do we have any questions on these basic front-end tools and what they are? No? All right. So we're gonna continue working on exercises in JavaScript. We don't have any more new material to learn pertaining to JavaScript. We're just gonna keep working through the exercises. All right. So now we're going to start off with average velocity. Oh, this is not the right window to have it in. Here. All right, so this method is going to take in an array of positions which you have traveled to at some point in time, and the total change in time over the course that you have made these positions. And then given this information, you are to return the average velocity of the trip. And the time is always greater than 0, so you don't have to worry about negative time. That's not a thing. So the definition of velocity is how fast you're moving, taking into account direction. So here we have the change in position divided by the change in time. So here we have all the positions. You need to find the net change in position over the course of the positions you have traveled to and divide it by the change in time. And the change in position is defined as your last position minus your first position, because that's where you ended up and that's where you came from. So that's the change. All right. Are there any questions? No? If not, I'll throw this in the chat. Let's see here. And I will put 10 minutes on the clock. All right, continue the recording. Average velocity. So we know that the change in position is the last position minus the first position. So we could say that the change in position is equal to the last minus the first. So in order to get the last index, we could take the length of the array and subtract 1. And that would give us the index of the last position. So we're going to take the position array at the position array length minus 1. So that gives us the last value. And we're going to subtract the position array at the first value. All right. So that gives us the change in position. And the change in time is simply the time given to us. So that means I could just return the change in position over time. So now let's write some tests real quick to verify that this is in fact correct. Head on over here and ask whether or not these are in fact equal. Console log or average velocity. And we should see 0.6 and 1. So I'm going to click run here. And we do, we get true for both of them. And we don't need to consider negative time. We don't have to consider 0 time. So we are good. Wait, are there any questions about this solution? No? All right, then I will move on to the next question. Our trip. Oh, and I will erase the solution here. So car trip, write a function that takes in a car object, which is an object that contains people, miles, and your spare tires used. So people is an array of strings, each of which represents a person. Miles is a number indicating the miles driven, and spare tires used are the number of spare tires that you had to use throughout the trip. You update the car object to include the new amount of miles on the odometer. So because we're updating the existing object, this is in fact going to be a mutating function. Additionally, the road is very rocky, so you'll need to use an additional spare tire every 1,000 miles. So every time 1,000 miles has passed, you will increase the spare tires used by 1. So you must update the car object to reflect this as well. So here we know that we have traveled 1,500 miles already and have 0 miles, but now we wish to travel an additional 5,500 miles. As a result, we will have traveled 7,000 miles and have used 5 spare tires in the process. Are there any questions? No? Then I will send a link in the chat. And I will see you in 15 minutes. All right, continue the recording. So as this is a mutating function, we can modify the object passed to us directly instead of creating a new object. So one thing we can do is we actually don't care about the people in the car. That doesn't change anything. So we can just ignore that component. But we do care about adding the amount traveled to the existing amount to get the new amount traveled. And for the amount that has just been traveled, we will increase the spare tires used for every 1,000. So if I traveled 5,500, that's 5, because it's not quite 6,000, but it's more than 5,000. So we would have gone 1 spare tire for each of those 1,000 miles. So now let's say I want to take our car, go here, and I want to take its miles, and I want to increment it by the miles we just traveled. Great. As for the spare tires used, we have to increment that. So spare tires, oh my bad, cars, spare tires used is incremented by the amount of miles traveled divided by 5. But if it's not a perfect multiple of you're going to get a fraction. So if I had 5,500 divided by 5, that's, well, divided by 1,000, because for every 1,000 miles, that's 5.5 tires. I can't put on 0.5 tires, so I have to round it down to the nearest integer. So this will become 5. So I can use the floor function to round it to the lowest. So I'm going to increment by math.floor on the miles that I just traveled, not the total miles traveled, divided by 1,000, because it's for every 1,000 miles. Good. All right. And after that is done, we then return the object that we just modified. So do keep in mind that mutating functions are allowed to return the modified object, although that is not necessary to get the results, as the object that was passed as an argument will have those results anyways. But so you can't tell whether something is mutating or non-mutating just by looking at its function signature, seeing what it returns. You still have to look at its docs, or alternatively look at the source code. So I can use this as a test, but remember, we can't compare objects directly using the comparison operator. So we can just manually look at it to verify that it is the correct output. So first I'm going to copy this. I'm going to paste it here. There we go. So I'm calling car trip with this object 5,500. So actually, this is another example of why it's a good idea to actually return the object in question, because here we never saved this object anywhere. We just passed it directly as an argument. So that means if I didn't, actually, like, let's say I take its result and I say, new object equals, or maybe let new object equals, that would allow me to actually store it and do stuff with the newly generated object. The existing object that we created here, but never stored in a variable in the first place. Right, great. So now let's run this, and we should see and people haven't changed, but it should say 7,000 miles and 5 spare tires. And it does, 7,000 miles, 5 spare tires used. Great. Are there any questions about this problem? No questions? All right. Then I will erase this. And we'll move on to the next question. Greatest common denominator. So now we're going into a recursion problem. There is an algorithm called Euclid's algorithm, which is used to find the greatest common denominator of two integers. And a greatest common denominator is the largest number that evenly divides another number. So let's say I want to, if I had two numbers A and B, it's equal to B if B evenly divides A. And it must be the greatest common denominator. It must be the result of this function, because otherwise it would be not the greatest. It'd be some other one. So if I had a number like, well, here I have 30, for example. What's the largest whole number that evenly divides 30? Is it 12? Well, no, not necessarily. So the formula is this: if B evenly divides A. So if it isn't the case, then you just have to pass it again, B for A. So the result that B was in the previous run, because this is a recursive function, it makes future calls to GCD. A becomes what B was, and B becomes A modulo B, the remainder of the division of A over B. And it does this so it can hone down until it receives a whole number. So you can write a function using recursion to implement Euclid's algorithm and return the greatest common denominator of two given integers. All right. Are there any questions? Great. I will send the link in the chat. And I will see you all in 15 minutes. Where are we? Here we are. All right. So the greatest common denominator is a recursive problem, and it finds a number, the largest number that evenly divides two given numbers, A and B. So the Euclidean algorithm is as follows. First, we must check if A is equal to B. If A is equal to 0, because if this is the case, then the greatest common denominator of the two is simply B, because the greatest common divisor of 0 and B is in fact B. Similarly, if B is 0, then the result is A, since the greatest common divisor of 0 and A is A. So I could just say if A, and if they're both 0, then it doesn't matter which one you get, because you get the same answer either way. So if A is 0, then I can return 0. My bad. Then I can return B. And else if B is 0, then I can return A. And if they're both 0, then both B and A would be the same answer. By the way, if and else if here isn't actually required, because if you return within it, then there's no continuing down this else if chain. It simply stops right then and there. So I could have just said if, and also because they're one line, I don't require these little braces. So just to keep it cleaner, there we are. Actually, we could put this in one line as well. Great. So these are our base cases. Now, we can make a variable, call it R, representing the remainder of the division of A and B, assuming that A is greater than B. And that is a perfectly valid assumption. If it isn't the case, then we could check which of the two is larger and then simply use that. So I can say, let R equal the division of A and B. And the division is A mod B, because that gives you the remainder of the division. That is what modulus does. So now I need to find the greatest common divisor of B and R, because the greatest common divisor of A and B is equal to the greatest common divisor of B and R. And you can keep doing this until one of them is set to 0. So now I can return the greatest common divisor of B and R. Now let's take this example right here and see to it that we do in fact get the answer we expect. In fact, we might also want to check subsequent calls for our values of A and B. So while we're in here, why don't we console log A and B? And we should see 30 and 12, then 12 and 6, and finally this is going to return 6. So if I run this, yep, 30 and 12 becomes 12 and 6, becomes 6 and 0. One of them became 0, and therefore we return our final answer. In this case, the first one was hit. The second one was hit because B was 0. So it returned 6, which was A. All right. Are there any questions? None? All right. Then I will delete this and move on to the next question. Let's see here. We have back of the line, an arrays and loops problem. Back of the line. I'm just going to copy this link right here. Open it up here. Delete this. So back of the line. I've already added some tests in here, by the way, as I was working on it earlier, and I thought I might as well leave them there. So write a function that takes in 2 arguments, an array of names and a number, which can be either negative or positive or 0. The number represents how many positions the names in the array should move, either to the right being positive or the left being negative. The expected output is the array of names. So it's the same names, it's the same length, but the names are in their new positions. So here we have an array of names in a specified order, starting with Kyle and ending with Greg. Here I'm saying shift them 2 positions over. So Kyle was in the first position, then it moved to the 3rd. Now for these guys over here, they have to go 1 and jump all the way to the beginning so that it shifts in a circle. So Greg would move over 1, 2. So that'd make Greg the 2nd. Kenesha moves 1, 2. Kenesha would be 1st. All right, great. Kyle moved 2. So now it's where Tina was. Stacy moved 2. Now it's where Kenesha was. So those are all moving to the right. -1, everything moves 1 to the left. So Stacy's 1st, Tina's 2nd, Kenesha's 3rd, Greg is 4th, and Kyle moves all the way back to 5th. All right. Are there any questions as to what this problem is asking us? No? All right, then I will send a link in the chat. And I will see you in 15 minutes. All right, so back of the line. So there are a couple of ways we can do this. One is with a map and one is with a for loop. The map solution was kind of a pain, so I think we're just going to stick with the for loop as that is the one that's most essential for you to be familiar with. So first of all, let's see right here, back of the line. Shift to 0. Yes. First, we're going to store the amount that we need to shift by into a new variable, simply because the amount that we want to shift by is not necessarily something we can apply directly, and modifications may need to be made. We can always represent a left shift as a larger right shift. For example, here, shifting 1 to the left is the same as shifting 4 to the right. So Stacy is the first. Stacy was initially the second. 1, 2, 3, 4. It looped all the way around, but 1 left. So 1 to the left is the same as 4 to the right. So this means all of them that involve going backwards can then be represented as going forwards. And the reason we want to do that is because if we want to access the element immediately to the left, we can't just say -1. No, we have to give it a positive index, because negative indexing does not work in JavaScript. Like here, I can have an array and I can say I want the 0th, or I want the first, or I want the second, which are the first, second, and third locations respectively. But I've asked for -1. It won't give me 3. It will just say undefined. That's not a thing. You can't do that. But I could say, I want to take the length, which is 3, and I want to subtract 1. And that will give me the last one. And subtract 1 because indexes start from 0, 1, and 2 respectively, because it starts at 0. So we could just increment by the length. That's another option. Additionally, when we go over the array, we might go out of bounds. We will go out of bounds. So we need to tell it to go back to the start. And we do this with modulus by saying if it wholly divides, it goes into all of them. And then I have 6. 6 over 5, that has a remainder of 1. It takes us back to the first, and we can keep looping around no matter how many shifts it would have had to take. So now we have all the building blocks laid out on the table. Let's first start with creating our shift amount. So shift equals the number of positions. But if our number of positions is less than 0, then I have to change that to in fact be the length of the array plus the number of positions, because remember, it's a negative value. So that means if I had -1, I would take the length and subtract 1 to it, because I add -1, and that gives me the last position as a right shift. So this effectively lets us transform a left shift to a right shift. Great. Next, and by the way, the reason why we had to make a new variable instead of just modifying number of positions directly is because then that would change this argument that's passed if it happened to be variable, and that would be an unintended side effect. So you have to be very careful about mutation occurring within your functions. All right, so next we have to make a copy of the array. But you know what? First, let's not do that, and we'll show you why it doesn't work. So let's assume we operate directly on the array and update the positions accordingly. So I'm going to make a for loop for let I equal 0, the index I, while I is in fact, oh, that's not supposed to happen. There we go. I is less than the length of the array. So we'll go over all the indices. We will increment I. Great. Oh, is that, yeah, that's good. So one thing I can do is I say I want to access the value to the right, the amount that's been shifted. And there's two things you can do. One is you can say, I want to take, if I want to shift to the right, which we do in this instance, I can say, take the value that is at our right and replace it with the value that was at the left. Or alternatively, I can say, take the value that is at your left and replace it with the value and override it with the value from that direction. So either way, you're shifting the values. And we're going to do the former. So I'm going to say, I want my array, and I want to get it at the position I, that's where it presently is, and then I consider the amount that I wish to shift it by. However, if that goes beyond, let's say we're at index 4 and I wanted to move it 2, well, then it's going to go into 6, and 6 doesn't exist. But if I mod it by the length, so array of names dot length, then I will actually go back to the beginning, 1, 2, because 6 mod 4 is 2. Because 6 divided by 4 is going to be 1 remainder 2. All right, after we do that, we need to set it to the value that was to its left. So the value that was to its left moved to the value that was at the right. So it overrode it, essentially. So I can say array of names. And I think you might be able to see the problem now. We're overwriting information. What was in this position is no longer there anymore. All right, to show you what it looks like. Yeah, we still need to return the array after we've made the changes. So you can see it. Additionally, this is also mutating the existing array. That's a secondary issue. But if we run this, we see what happens. You know, we have for 0, nothing's changed because it's just writing to the same position. But here we see Stacy, Kyle, Kyle, Stacy, Kyle. That's because when we want to move this 2 over, it overwrote what was there. And they all overwrote each other. So now the value that it's taking from its left was a value that was previously copied over from its left. So it's just copying the same value over and over again. So we have to make a new copy of the array. So I can say, let new array be a copy of the original array. Great. Now I'm going to apply changes to the new array. And we're going to reference from the original because that data has been preserved. If I tried to get it from the new array, well, 1, it wouldn't be there, and 2, it would be a mutation, which is something we cannot abide by. All right, after that's done, we now have to return our new array instead of the old array. And now when we run this, we do in fact see that for 0, it remains unchanged, but we do start with Kenesha and Intina, and we start with Stacy and end with Kyle. Great. Do we have any questions? No? All right. Then I will delete this. And I think now is a good time to take a 10-minute break. So I'm going to put 10 minutes on the clock. And I will see you then. All right, so our next problem is called palindrome. It's a recursion problem. I'm just going to copy that link. And over here. So the problem is this: write a recursive function, which means a function that calls itself, that takes in a string, the parameter of which is called word, and determines if the string is a palindrome. Well, what's a palindrome? A palindrome is a word that is written exactly the same forwards as it is backwards. If it is a palindrome, return the Boolean true. If it is not a palindrome, you would return false. So here we can see an example of a palindrome, race car. If I look at that backwards, R-A-C-E-C-A-R, that is also a palindrome. It's also the same word. Therefore, this word is a palindrome. Whereas a word like conifer, if I read that backward, that'd be refinok, which is not conifer. So this is not a palindrome. All right. I added some tests here already. I'm gonna go. Does anyone have any questions about this? No? All right, then I'll put this in the chat. And I'll put 15 minutes on the clock, and I will see you then. Oh. All right, great. So recursion. So As with all recursive problems, we require a base case. I think a fair situation is we could take an empty string, which forward and backwards is in fact the same. So naturally, we could say if the word is an empty string, return true. There we go. Now, one thing I could do is I can compare the first letter to the last letter and check that they are equal. Okay, that's great. So we're off to a good start. Now the next one, and we do this iteratively until we go through all the letters, but we can't iterate, we're going to have to use recursion. So I can check the next letter by making a call on a subsection of the word that excludes the first and the last letter. And I can keep doing this until I have an empty string, in which case it will return true. And if we catch at any point it does not equal, we simply return false and we never reach this case. So I guess that's the other situation here. The other case which would exit out is determining that they are not in fact equal. So first I can say if the word at the first index, and I can't just say last index directly, I have to say word at the word length -1, which is how we access the last one. If that is the case, then we can return false. And lastly, we want to return what happens if I compare the first one to the last one. My bad. If it does not equal, then it returns false. Else, they are equal, and now we can look at the last, at the subsection of the word. So how do we get the subsection of the word? We can use slice. Let's go to the console real quick. Let's say I have a word like race car, and I can slice it from the first element, which means excluding the very first one because it starts at 0, remember, and up through -1, which is the last element. And that gives me ace-ka. And now I'm just going to say is A equal to A, and it works in and out. It works until it gets all the way to empty. So now I'm just going to return palindrome on the word, the subsection of the word from 1 to -1. Now, another thing is slice actually does allow you to use -1. I should mention that, but direct indexing does not. So I can't directly index the word, but if I want to make a new string using a subsection of the word, negative indices are permissible for this particular method. All right. Having said that, let's give this a run. And we are in fact getting the expected outcomes. Race car returned true, and palindrome of conifer returned false. Are there any questions about this problem? No? All right, then I will delete this and move on to the next problem. That would be the Fibonacci sequence. All right. Write a recursive function that takes in a number and returns the associated number in the Fibonacci sequence. The sequence begins with 0 and 1. Then the next number at any point in the Fibonacci sequence is formed by adding the previous two numbers together. So we start the sequence with a 0 and a 1. The next number 1 is equal to 0 plus 1. The next number 2 is equal to 1 plus 1. 3 is equal to 2 plus 1. 5 is equal to 3 plus 2, and so on indefinitely. So we need to find the nth number in the sequence. So the third number string is 0, 1, 2, 3. Okay, so we're starting from 1. So 1, 2, 3, the third is 1. So just to be clear, this index is starting from 1. That is the behavior that is specified. This is the third element, this is the 7th element, this is the 16th element. You do have to be careful because sometimes it's more intuitive for people to think of starting from 1. So very often that will be the behavior of many methods. However, in JavaScript, naturally, a lot of things do begin indexing at 0. So we have to take that into account when we create our programs. All right. Do we have any questions about this problem? No? All right. Then I will post this in the chat. and I'm going to put 15 minutes on the clock, and I will see you then. All right. So Fibonacci sequence. Well, we know that the first two numbers are going to be 0 and 1. So that's going to be our base case. If the sequence number in question is 0, then it'll return 0. If it's 1, then it returns 1. So I have to have both of those in there. If sequence equals 0, well, actually, you're starting from 1, right? Because what's the first element in the sequence? Then it returns 0. If we're looking at the second element in the sequence, it returns 1. All right, cool. Now, the reason why this is explicitly required is because even though this would be a sufficient base case for moving on, the fact that they can provide this value directly means that it must be provided, because 1 plus 0 is still 1, so it would still work the same. So one thing I do know is that I'm taking the previous two values, so it's just the value before and the value before that, and those values are in turn determined by their previous values, and that's where the recursion comes in. So I'm able to add the previous two values in the sequence, which are retrieved using this function. So I want the Fibonacci of sequence -1 added to sequence -2. Those give us the last two. And I know that we'll have two values to refer to because we have two values that it is going to be able to return. So if I gave you 3, it would say, okay, find the Fibonacci of 2 and 1. Well, 2 is 1 and 1 is 0. So they would add together to give you 1, which is the result here. Similarly, and it works here. It has to compute 3, and it uses that by computing these two. So it's not a very efficient algorithm. There are much more efficient ways to do this because it's going to make the same calls over and over and over again. But it does work. Why don't we write some tests real quick? We want to ensure that these are in fact equal. For very large values, this would be unacceptable. But for the purposes of demonstrating recursion through the Fibonacci problem, I would say it is sufficient. Yeah, so they all pass. Do we have any questions about this problem?
Yeah, I got a question.
Sure.
So now, so explain line 4 again for me, please.
Okay. So the Fibonacci function returns the value in the Fibonacci sequence at the specified position. And Fibonacci is, by definition, the sum of the previous two values in that Fibonacci sequence. So the first two lines are just returning 0 and 1. So the first one is 0, the second one's 1. But now I'm like, okay, the third value, that's what I requested, Fibonacci of 3. What is it exactly? Well, it's going to be the previous two values, 0 and 1. So to get them, I need to access those particular locations. So the current sequence is 3. 3 minus 1 gives us 2. And 3 minus 2 gives us 1. So now I'm trying to sum the results of Fibonacci 2 and Fibonacci 1, which are these two values respectively. And they are returned from the function. Similarly, let's say I had 2 here, and I wanted to sum the previous two values. So that's the first, second, third, fourth value in the sequence, so sec of 4, which is going to equal 2. And I could show that real quick. Actually, I could probably console log what's coming in, so you can see what's actually happening. So console log sec. And let's only look at one example so that we don't get overwhelmed by the numbers. Here, you see that we actually go through a lot of numbers in the process. First, we have 7, and it's like, okay, 7 is going to be the result of 6 plus 5. Okay, in order to calculate that, we need to calculate 4 and 3. In order to calculate 4 and 3, we need 2 and 1. And you can see that this is what I meant when there's a lot of making the same calls over and over again. And actually, if I can show you a picture real quick, Fibonacci tree, that'd probably be a lot more helpful to explain why this is not ideal. So like here, I want to calculate 5, right? Like I want to find the fifth in the Fibonacci sequence. That's going to be the sum of the fourth and the third, right? But to calculate the third, I need the second and the first. And the second is just 1 and 0. So that's pretty straightforward. But here you'll notice that to calculate 4, I need to calculate 3 again and 2 again. So I'm doing a lot of the same computation over and over again, which is why it's not an efficient implementation. Although you could simply save the result and then reuse it. That's called memoization. So we have to calculate those previous values, and that's why it makes the call again. To calculate Fibonacci of 5, I need Fibonacci of 4 and 3, and then I add them together. So that's why I'm taking the previous two values and adding them together on the fifth line here, what was the fourth line.
Oh, okay. Okay, I understand.
Yep.
I got it. Appreciate it.
All right, and we have no other questions. I will just delete this. There are many different approaches to the Fibonacci problem, and some are better than others, unequivocally. But this one was by far the easiest way to explain it, because the other ones get pretty long. All right, moving on to the next problem. That's gonna be hungry hippos. The raisin lips. All right, let's put this in here. So you're playing a game of hungry hippos with 3 other people. And I don't know if you're all familiar with hungry hippos. I can't spell. It was a fun little game, a tabletop game with hungry hippos. These little things where there's all these pellets in the middle and you press the lever and it'll eat the pebble. Right. So, and the objective is to eat as many as possible. So you just spam the lever. There's 4 players, and it's a given fact here. They're saying that each of the 4 players, which are identified as 0 through 4, will eat a specific number of pellets in each turn. So player 0 eats 3 pebbles, player 1 eats 4 pebbles, player 2 eats 6 pebbles, and player 3 will eat 1 pellet. In that order, always. And it happens every single time. And it just keeps repeating. The game ends when there are no pebbles left. So we can write a method that takes in the starting number of pellets. So these are how many pellets are available on the board. And then we're going to return an array because we want to get 2 values out of this function. The first is going to be what turn the game ends on. So we're going to keep track of the turns. And just, 4 people work in 1 turn. So they're all going to go in that turn. Then the second turn, that's them going again. Third turn. So that might have caused a little confusion. I just want to clarify that 1 turn isn't 1 player. It's all the 4 players getting 1 turn to actually go in. And then we actually want to, in the second value, return containing the turn of the game and which player eats the pellet last. So remember, each player is numbered 0, 1, 2, and 3. So the last one who was able to eat pellets will be returned. And remember, we may not complete an entire turn, which has all 4 players, because let's say the first 2 ate and now we have, we've got less than or equal to 0 pellets available on the board. So naturally, the next player would not be able to eat any pellets, so it would stop and return that player. All right, and there are various array methods available to you. You do not require them, but they are there. Right. Do we have any questions? So here we have Hippo 1. So there's only 1 pebble on the ground. The first player eats it because he's able to eat up to 3 pellets. He eats only 1. And so it ends on the first turn because we're during the first turn and then it stopped. And it ended on player 0. And we're starting with player 0 and working our way around. All right. So if we don't have any questions, I will place this in the chat. All right. and put 15 minutes on the clock, and I will see you then. All right. So let's see here. Yes. So first of all, we cannot mutate the number of pellets, even though we do need to subtract from it, because that could affect a variable if it was passed into here. So I would say I want to create count, which is in fact equal to the value of num pellets. And when you use the assignment operator on a number, it will not refer to the original value. All right, great. So now we also want to keep track of our turn so that we can return it. We're going to want to store the amounts to eat for each player. And because the players are just 0, 1, 2, 3, and 4, we can associate those with the indices. And as a result, we do not need to create an object. So I can just say, this is a constant because it's not going to change, amounts to eat, amounts to eat for each of them is going to equal an array of, let's see what this is, 3, 4, 6, and 1. 3, oh, there we go. 3, 4, 6, and 1. We can also remember that the number of players is going to equal the length of our amounts to eat array, which is 4. All right, with that all said and done, we have to iterate over every single turn. So I can say, and we already declared turn, so turn is set to 0. While turn is less than number of pellets, because number of pellets, num pellets, yes. So hypothetically, it would be possible that only 1 pellet was consumed per turn. So these amount to eats might have varied dramatically, but there can be no more turns than there are number of pellets, even if only 1 person ate a pellet each turn. Similarly, if no one ate any pellets any turn, then this game would never end, and this loop would just go on indefinitely. So yeah, the amounts to eat must contain at least 1 positive value for this to ever end, which I think is a reasonable assumption. There might be this one player who really sucks at the game and just never gets any turn, which is very unfortunate for that person. All right, and then we're going to increment the turn every single time. Now, for each turn, every one of the 4 players needs to be able to have a turn to eat. So we're going to make another for loop inside of it. We're going to have p for player equals 0. I can say while that player is less than the number of players, we're going to increment our current player. All right, cool. And we are going to decrement on the count, not on the num pellets. So count is going to decrease by the amounts to eat at our player. Oh, yeah, but it's not just that. It's the player mod the number of players. That's not necessary. Yeah, because it only goes over the number of players. It's never going to go over, so modding is not necessary in this case. All right. So now if the count is less than 0, then, well, we know, and we can check this after every single player. We want to check, is our count less than 0 or less than equal to 0? Because if it is, then, we can't continue the game any longer. So I can say if the count is less than or equal to 0, then we can do the following, and that is return. We need to get the current turn. Now, the player turn is not the same as this here. So this actually runs, once for every time. This happens 4 times. Okay. So what we can do is just divide that value by 4 and add 1, and then take the CL of it, which rounds it up to the nearest value. So again, we need to return an array, and it's going to be math.ceil. And there are alternative ways to do this. You could have just kept the turn count within the inner for loop instead, and that would have been equally valid. That's 1. And then we're going to want to know the current player, which is simply P. All right. Oh, and again, this should be the number of players, which just happens to be 4. So number of players plus 1, P. So what I've done in this design is made it so that if I wanted to add an additional player, all I'd have to do is specify where they are in this position. So it's a much better design in that regard, rather than hard coding 4s everywhere and numbers to eat. Like you could have just had 4 if statements after every single decrement of the count, and then manually incremented the turn after all 4 have gone. But that is that's a worse design because you're repeating code. All right, so after that's said and done, it will break the for loop when it returns. So now if I run this, yep, we are in fact getting 1, 0, 1, 2, and 2, 1. So this does work. And I didn't use a comparison operator here because, again, comparing arrays doesn't work that way because this is a newly generated array being compared to this, which is not fair at all because they're not referring to the same array. All right, are there any questions as to this problem? No? All right, I will delete this. And let's see, how much time do we have left? We have 10 minutes, and it takes 15 minutes to finish a problem. So I think we are done for today. Let me just stop the share. We have our last meeting tomorrow, and we're not going to be covering any new content. We're just going to finish up the remaining exercises and answer any questions. And however long that take, it might be a much shorter lecture than the ones we've had previously. All right. On that note, I'm going to stop the recording.